Before you start attending your technical interviews, make sure you really understand about algorithmic complexity. Trust me, it will absolutely come up. But what is it, and how about time and space complexity? Oh, and what's all the fuss about big O notation? If you are having such questions in mind, stay tuned as we explain everything on various complexities of algorithm in the most simplified way to understand. Let's get started. Alright, so we'll start by exploring why we need algorithmic analysis and also look into the various ways of measuring complexity like time and space complexity. Next, we'll introduce the much awaited term big O and go through some of the notable complexities like order of n, order of n square, order of 1 and order of log n by analyzing plots on graph. In the end, we'll wrap it up by sharing our takeaways and grasp of the concept through the lens of big O. Imagine we have two pieces of code, code 1 and code 2, both doing the same thing but written differently. Now, how will we figure out which one is better? Let's use a stopwatch. We run code 1 and it takes 15 seconds. We reset and run code 2, which takes about a minute to complete. Obviously, we want the faster and most efficient code, so code 1 wins. This whole thing is called time complexity. But wait. Hold on. We generally don't measure time complexity in seconds. Instead, we measure in terms of the number of operations. But why? That's because if we run the same code on a faster computer, it finishes in less time, but the number of operations remains the same. Irrespective of whether it's a supercomputer or an old computer, the number of operations is gonna remain constant. Besides time complexity, there's another concept called space complexity. Space complexity measures how much memory an algorithmic code uses. Say for example, our code 1, which finished in 15 seconds, takes a lot of memory, while code 2, which took almost a minute to complete, uses very less memory. So, if memory consumption matters more to you, then maybe code 2 is better. This is space complexity. Stepping into big O. Fine, let's break it down. When you start digging into time and space complexity of algorithms, you'll come across terms like big O, theta, and omega. Don't stress, it's not as complicated as it sounds. Let me explain you with a simple example. Imagine it's your mom's birthday and you promise to cook her favorite dish. She's excited and asks how long it will take. Now, what do you tell her? Realistically, it depends on two things. One, how experienced of a cook you are, and two, whether all the ingredients and prerequisites are at home or if you need time to go shopping. Let's consider the availability of ingredients point for now, and based on that, we have three situations. Best case, all ingredients are at home and you just need to whip up the dish quickly. Average case, some ingredients are at home and others need to be bought. It's kind of a middle of the road situation. Worst case, no ingredients are at home and you need to buy everything from the shop now. This takes the longest time. Just like these three cases, while analyzing algorithms, we use three Greek notations to represent what's the complexity level in best, worst, and average case. We have omega representing the best case scenario. It represents the best time and space complexity when everything is perfect. Theta represents the average case, which considers both good and bad situation. Third, omicron or big O is the worst case scenario, the maximum time and space complexity when everything goes wrong. We often focus on omicron or big O because it gives us the worst case scenario, helping us analyze the maximum limit an algorithm can hit in terms of time and space when things go all unfavorable. Remember those algebra functions from 12th grade like y equal to f of x or y equal to f of x square or y equal to f of 2x plus 3? We used to plot them on graph paper with 4 quadrants, right? Now think of big O as a similar graph function but exclusively for algorithms. Instead of x and y, it has size of input n on the x-axis and number of operations big O on the y-axis. As we agreed that time complexity is all about the count of operations, we are interested in how the number of operations, that's big O, changes when the input size n changes. Big O is like the superhero of worst case scenarios. Thus, it's a mathematical way of representing how efficient an algorithm is by showing how its operations behave when everything goes wrong. Some big O representations you might see are order of n squared, order of n cube, or order of 1. Let's discuss few big O representation in detail. Let's jump into our first big O notation, O of n. Think about chopping vegetables in your kitchen. If you have a few vegetables, it's quick to chop each one. The more vegetables you have, the more time it takes because you got to chop each one. Doubling the amount of vegetables for a dish roughly doubles the chopping time. It's like a straight line. More vegetables, more time. Now, let's talk about a simple function called display. It takes a number, let's call it n, and it prints hello world n times. If n is 1, it says hello world once. If n is 2, it says hello world twice. If n is 100, it prints hello world 100 times and so on. Here, the operation is printing. Now, we have two sets of values. The number of operations and n are input size. We are going to put them on a graph. On the x-axis, we have n, that's our input size, and on y-axis, we have the number of operations, our big O. When we connect the points on the graph, guess what we get? A straight line. Oh, we all know this from 12th standard maths that this is the line y equal to f of x, where if x equal to 1, y equal to 1, if x equal to 2, y equal to 2, if x equal to 3, y equal to 3 and so on. So this is the same. So instead of y equal to f of x, let's switch it up and say big O equal to O of n. It's just another way of saying the same thing. Easy, right? Let's dive into our next big O notation with a yummy example. Imagine you have 5 flavors of ice cream: mango, vanilla, strawberry, chocolate and butterscotch. If you want to taste every possible combination of 2 flavors, it's like a little operation inside an operation. You taste mango with each of the other 4 flavors, then taste vanilla with 4 others and so on. Now, similarly, think about a nested loop function called logger. It takes a number, let's say n, and goes through loops to print numbers. The print statement runs as many times as the nested loop runs, and the nested loop depends on the number n, which is taken as the input. If n is 10, it's like an outer loop running 10 times and an inner loop running 10 times for each run of the outer loop. Thus, 100 times the print statement is done. If in case n is 100, each loop runs 100 times, thus totally 100 into 100, 10,000 times the print statement is executed. When we put these values on a graph, it's like a curve, like y equal to f of x square. In big O terms, it is order of n square. Now, let's compare both order of n and order of n square on the same graph. Order of n seems to be better because for the same n, order of n is smaller than order of n square. That means if n equal to 2, order of n is 2 while order of n square is 4. So if you have 2 algorithms for a given problem, one with order of n complexity and one with order of n square complexity, the more efficient one is the one with order of n complexity. Our next big O notation is O of 1. Imagine you have a basket of fruits and you want to grab one. Whether it's an apple, banana, or mango, the time it takes to grab any fruit is the same, no matter how many fruits are there in the basket. That's what we call as O of 1 complexity. Now, think about a method that would simply give you back whatever you put in, whether you give it 1, 2, 10, 100 or 1000. It always takes just one step to return it. This is the magic of O of 1 complexity. Picture this on a graph and you'll see a straight flat line at the bottom. Compared to other complexities, this is like the superhero of efficiency. Nothing can beat O of 1 complexity. It's the most efficient. We even call it constant time because it always takes the same amount of time no matter what. Imagine you have 8 closed boxes containing numbers from 1 to 8 in ascending order. Let's say you want to find the number 7. One option is you could check each box one by one. But what if you had 1000 boxes? Checking one by one would take forever. So, here's a smart move. Since the boxes are in order, start in the middle. Is 7 greater or lesser than the middle number, which is 4? Well, it's greater. So you know that it's in the second half. You discard the first 4 boxes and search again in the next 4. So you keep repeating and dividing the remaining half until you find number 7. Now instead of 8 boxes, imagine if you had 1000 boxes. By doing this smart trick, you quickly discard about 50% of the boxes. Now let's count the steps it took. 1, 2 and 3. So for 8 boxes, it took 3 steps. This is like the math relation called logarithm. Here, log base 2 of 8 is 3. It tells us how many times we split the total number by 2, that is into 2 halves, to find our value. This smart trick is called divide and conquer, where we keep dividing until we find. When we plot this on a graph, it's a very flat line. Not as flat as our superhero order of 1, but way more efficient than order of n and order of n square. We'll check out some example code for order of log n later on, along with specific algorithms. But for now, let's stick to the understanding of main idea. Thus, to conclude, understanding algorithmic complexity, especially through the lens of big O notation, is a valuable knowledge in the world of programming. We have explored various complexities, starting with the lightning fast order of 1, moving through the linear order of n, and diving into the efficient order of log n. Each notation tells a story about how algorithms perform as the input size changes. Remember, big O is not about measuring seconds or minutes. It's about understanding how our algorithms scale. It's like looking at the big picture of efficiency. Order of 1 is the superhero completing tasks in constant time. Order of n is linear, scaling with input size. Order of log n is the clever divide and conquer, swiftly solving problems in a sorted dataset. And yes, there are even more big O notations out there. You can dive deeper into this at www.bigocheatsheet.com. It's a cool place to get insights on big O for different data structures and algorithms. Do check it out. I'll put the link below in the description. Thus, big O is not just a notation. It's a guide to write more efficient, scalable, and powerful code.